We now discuss how the moments of inertia of plane lamina about different axes are found. Here we have a question where you need to find the moments of inertia of this given composite lamina about its centroidal XX and centroidal YY axis. As you see, the first step is to determine where the centroid is. You have to locate the centroid of this lamina before proceeding with the problem. Now, so as to find the centroid of this lamina, as we discussed earlier, you have to split this composite figure into known geometric shapes. As you see, this lamina is composed of a rectangle of dimensions 2 cm by 6 cm. We'll mark it here. Figure number 1, a rectangle. And we have a semicircular portion that has been cut off or removed. We'll name it as figure number 2. We have another rectangle of dimensions. How much is it? 4 minus 2, 2 cm by 3 cm. Let's name it as figure number 3. And finally, a right triangle of base 2 cm and altitude 3 cm. Figure number 4. So, as you already know, you have to first locate the centroid of the common lamina, composite lamina, by considering the moments of areas of all these individual shapes about a reference axis system. And let's choose, as we have done earlier, the lefternmost axis as the reference y-axis and the bottommost axis as the reference x-axis. Now let the area of the first figure be A1 and the centroidal distance, where's the centroid? Here, right? The figure number 1 has a centroid here, and for this figure number 2, this is a semicircle, and we know that the centroid is at a distance of 4r by 3 pi from the diametric segment. And for the figure 3, it is the intersection of the diagonals, a rectangle. And for the figure number 4, it's a meeting point of the centroidal axis, where this is h by 3 and this is b by 3. So these are the centroids of the individual figures. And let the centroidal distances from the reference axis be x1, y1 of A1. And for A2, figure number 2, let the area be A2, centroidal distance be x2, centroidal distance be y2, and so on for the respective portions shown in figure. Now what is A1? A1 is 2 by 6, 2 by 6, 12 square centimeter, and x1 is, as you know, the distance of the centroid from the reference lefternmost axis. How much is that? 2 by 1, it is 1 centimeter. And y1 is, how much is that? 6, so it is 3 centimeters. And for the second figure, figure number 2, it's a semicircle. The area is, the radius being, diameter is 2, the radius is 1 centimeter. So it is pi into 1 square by 2, 1.57 square centimeter. x2 is distance of the centroid from the lefternmost axis. It is 4r by 3 pi, 4 into 1 by 3 pi, 0.42 centimeters. And y2 is the distance of the centroid from the bottommost axis. It is 1 plus 1, 2 centimeters. Similarly, we can find A3 and A4. A3 is, this is 2, this is 3, 2 by 3, 6 square centimeter. X3 is how much? This is 2 and this is 1 centimeter. So the distance from the lefternmost axis to the centroid is this much is 2 plus 1. 2 plus 1 is equal to 3 centimeter, and y3 is the distance from the bottommost axis, and that is, the whole is 3, so it is half of 3, 1.5 centimeters. And for the fourth figure, the area is, it's a right triangle, the area is half into base into altitude, half into b into h is equal to half into 2 into 3 is equal to 3 square centimeter. And x4 is centroidal distance from the left turnmost axis, which is 4 plus 2 by 3, 1/3 of 3. 4 plus 2 by 3, it is 4.67 centimeters. And y4 is distance from the bottommost axis, it is, the height is 3, 3 by 3, it is 1 centimeter. So we know that x bar is equal to, as you have seen earlier, sigma ai xi divided by sigma ai, where ax is the moment of the area about those reference axis. So it is a1 x1. Algebraic sum, semicircle has been cut off, so it is minus a2 x2 plus a3 x3 plus a4 x4 divided by, again, a1 minus a2, it has been cut off, plus a3 plus a4. So you get it as 2.23 centimeters from OY axis, centroidal distance. And similarly, you can find y bar as sigma ai yii divided by sigma ai is equal to 2.31 centimeters from OX. So we find that the centroid is somewhere here, and the question is to determine the moment of inertia of this given lamina about the axis passing through the centroid, x-axis passing through the centroid. This is the x-axis axis, and the y-axis passing through the centroid, vertical axis passing through the centroid is the y axis. So this is the x-axis axis, centroidal x-axis axis, and this is the centroidal y axis. This is what ix and iyy, which you are supposed to find out. Now in the question, since we need to find the moment of inertia of the whole sections about this centroidal common axis, what you have to find is moment of inertia of the first portion, figure number 1 about x-axis axis, moment of inertia of figure 2 about x-axis axis, and 3 and 4, all of them about the x-axis axis should be found and algebraically added. Or rather, if the moment of inertia of the first figure about this x-axis axis is ixx1 and that of the figure 2 is ixx2 and of 3 and 4 are respectively ixx3 and ixx4, then the total ixx of the composite lamina ixx is equal to algebraic sum of all these, or 1, 2, 3 and 4, the moments of inertia have to be added algebraically. You get it as ixx1 minus ixx2 because portion 2 has been cut off. So it has to be deducted, subtracted. ixx2 plus ixx3 plus ixx4. This is what you have to find. Now what is ixx1? ixx1 is the moment of inertia of the portion 1 about an axis. This is that axis, about an axis which is parallel to its own centroidal axis. This is its own centroidal axis, this being the centroid of portion 1. This is the centroidal x-axis axis of the figure 1. Moment of inertia of a rectangle about its own centroidal axis is given as BD cube by 12. You already know this. The axis which we are talking about now is another axis which is parallel to this axis and at a certain distance from it. Or this is a parallel axis to the own centroid axis of figure 1. So here we have to apply the parallel axis theorem and find the moment of inertia of 1 about xx axis, or rather Ixx1. This is a parallel axis to its own centroidal axis. So applying the transfer theorem or the parallel axis theorem, you can write that Ixx1 is Igx1 plus area into distance square. The area is A1 and the distance between the two parallel axes, the perpendicular distance between the two parallel axes, or this distance is H1. Is it clear? So you are applying the parallel axis theorem to transfer the moment of inertia of the first rectangle to the common centroidal axis. For transferring this, we are applying the parallel axis theorem, and the parallel axis theorem states that moment of inertia about a parallel axis is given by the sum of the moment of inertia about the centroidal axis plus the product of area and square of the perpendicular distance between the two parallel axes. So now things becomes much easier for us. We just need to find the distance, the perpendicular distance between the two parallel axes. So for that, you consider the centroidal axis and the own centroidal axis of the figure of the area which we are now taking into account. So this is the centroidal xx axis of 1, and this is the common centroidal axis, and this is the distance which you have to find. What is y bar? Y bar is the distance from the bottommost axis to the centroidal axis which you have found now. Now, what is the distance from the bottommost axis to the centroidal axis of figure 1? This is the y1 which you had calculated earlier. This is y1 and this is y bar. Then what is h1? h1 is obviously y1 minus y bar, right? Similarly, for the figure 2, this is its own centroidal axis, and this distance is y2. Now, the common centroidal axis and its own centroidal axis both are parallel. So, distance between the two parallel axes is h2. Now, what is h2? h2 is y bar minus y2. So, you get h2 is equal to y bar minus y2. And in the subsequent cases for 3 and 4, you find that the distance between the parallel axes is either y bar minus y or y minus y bar, as the case may be. So in a generic format, you can write the h in the parallel axis theorem is actually mod y bar minus y, or absolute value of y bar minus y. Clear? So this is what we are going to determine next. So now for the first figure, Ixx1 is equal to Igx1 plus a1 into x square, and Igx1 is equal to, how much is Igx1? It's a rectangle, and this is BD cube by 12. So it is equal to BD cube by 12 is equal to 2 into 6 cube by 12 is equal to 36 centimeter raised to 4. Right? Now h1 is equal to absolute value of y bar minus y1 is equal to, y bar was 2.31, and the y1 is, we have already found, y1 is 3. So absolute value of 2.31 minus 3 is equal to 0.69 centimeter. Now Ixx1 is equal to 36 plus area was 12 into 0.69 square is equal to 41.71 centimeter raised to 4. And for the second figure is the semicircle. For the semicircle is oriented like this. Here's the centroid. So this is the axis which we are talking about, the axis which is parallel to the centroidal x-axis. And for a semicircle, this moment of inertia is pi d raised to 4 by 128. And so you get Igx2 is equal to pi into diameter is 2 pi d raised to 4 by 128. 0.39 centimeter raised to 4, and H2 is absolute value of y bar minus y2 is equal to 0.31, and hence we find Ixx2 is equal to Igx2 plus A2 into H2 square is equal to 0.54 centimeter raised to 4. Now for the figure 3, Igx3 is again BD cube by 12. It is 2 into 3 cube by 12. And the H distance is, H3 is absolute value of y bar minus y3 is equal to 0.81. And you get Ixx3 is equal to Igx3 plus A3H3 square is equal to 8.44 centimeter raised to 4, because it was also a rectangle. And for the fourth figure, it's a right triangle. So this was the centroidal x-axis, and the moment of inertia about the centroidal x-axis, Igx4 is BH cube or BD cube by 36 is equal to 2 into 3 cube by 36 is equal to 1.5 square centimeter, and H4 is absolute value of y bar minus y4 is equal to 1.31 centimeter, and then you find Xx4 is Ig_y4 plus A4H4 square is equal to 6.65 centimeter raised to 4. Now that we have found the moments of inertia of all the 4 components of this composite lamina about the common centroidal axis, you can write that Ixx is equal to Ixx1 minus Ixx2. Why? Because portion 2 has been cut off, plus Ixx3 plus Ixx4 is equal to, you get it as 56.29 centimeter raised to 4. Now that we have found out all the moments of inertia about the x-axis, we'll move on to those about the y-axis. Just like what I have done earlier, you consider each of the component figures one by one. And for the first figure, this is the moment of inertia about its own centroidal axis. It is dB cube by 12. And the parallel distance between the two axes, this is the its own axis and this is the common axis. So this is the distance which we are talking about. Let it be h1 dash. And since this distance is x1 and this distance is x bar, just like what we have seen earlier, this is x bar and this is x1. The parallel distance h1 dash is absolute value of x bar minus x1. So Ig y1 is equal to dB cube by 12, or 6 into 2 cube by 12 is equal to 4 centimeter raised to 4, and h1 dash, the distance between the two parallel axes, its own centroidal axis and the common centroidal axis, is absolute value of x bar minus x1 is equal to 1.23 centimeter, which gives you Iyy1 is equal to Igy1 plus A1 into h1 dash square, applying the parallel axis theorem, and get it as 22.15 centimeters raised to 4. And for the second figure, this is its own centroidal y axis, and the moment of inertia about that is 0.11 r raised to 4. So you get Igy1 is equal to 0.11 r raised to 4. Sorry, Igy2 is equal to 0.11 r raised to 4 is equal to 0.11 centimeter raised to 4, 1 being the radius, and h2 dash is x bar minus x, and you get it as h2 is 1.81, and therefore Iyy2 is, applying the parallel axis theorem, Igx2 plus A2h2 dash square, you get it as 5.25 centimeters raised to 4. And for the third figure, the rectangle, it's again, this is the axis which you are considering, and this is dB cube by 12. So Igy3 is equal to 3 into 2 cube by 12 is equal to 2 centimeter raised to 4, and h3 dash is equal to absolute value of x bar minus x3 is equal to 0.77, from which you get Iyy3 is equal to Igy3 plus A3 h3 dash square is equal to 5.56 centimeter raised to 4. Now for the fourth figure, the right triangle, this is the centroidal y-axis, and though that for the x-axis was a bh cube by 36, so this would be, let it be d, we won't confuse d and b, let the formula be bd cube by 36, then this would be db cube by 36, and we have Igy4 is equal to db cube by 36, 3 into 2 cube by 36. See, this was 2 into 3 cube, this is 3 into 2 cube by 36 is equal to 0.67 square centimeter, and h dash 4 is equal to absolute value of x bar minus x4 is equal to 2.44 centimeters, and therefore Iyy4 is equal to Igy4 plus A4 h dash 4 square, and you get it as 18.53 square centimeter. Now therefore the total Iyy of the composite lamina is Iyy1. Now this is cut off, so it is minus Iyy2 plus Iyy3 plus Iyy4, which is equal to 40.99 centimeter raised to 4. Is it clear? So we have transferred all the moments of inertia about its own centroidal axis to the common centroidal axis of the lamina using the parallel axis theorem. The only problem which you face is to determine the distance between the parallel axis right from the first step. So for that, what we have done is the base which we have adopted for all the calculations being the same, the extreme left and the extreme bottom, you won't have a problem to find the parallel distance, which is always the absolute value of either y bar minus y or x bar minus x.